Welcome to Mastering Solutions. This question is a little bit involved, so let's first start off and make a list of what we know and just work through it one step at a time. They tell us that we have a diffraction grating, and so the diffraction grating spacing D, they tell us is 500 slits per millimeter. So in 1 millimeter, 1 times 10 to the negative 3 meters over 500 slits. We've talked about this in a lot of problems, and you know what I'm going to say. A diffraction grating D is always the width over the slits. Let's leave this just like that and move on to the next one. We're told that we have a single wavelength of light. And when they come over here and they tell us that there are 2 bright fringes observed, or several, they say bright fringes with these angles, we know that they're different M values because we only have one wavelength. We don't have to worry about if this is M1 for one wavelength and M1 for another wavelength. It's all the same light, just the single wavelength. So we don't know what the M is though. We have to figure that out. And ultimately, what we're trying to solve for is the wavelength. We want to figure that out. This is our whole goal, right? So how do we get there? This isn't a whole lot of information to go off of. Let's actually write this down. So theta 1 is 45.7 degrees and theta 2 is 72.6. So what we have to do is we have to think about this logically, because what would be the equation that we would be using to solve for lambda? What we could do is we could use the equation sine of theta is equal to m times lambda over d. We have d, we don't have m though, right? So we have to use this though to figure out m and to solve for lambda. If you think about the logic of this, they tell us that the first bright fringe is this degree and the one right next to it is this angle. So we know that whatever m this is, whatever order this bright fringe is, this one is the one right above it, right? So m is going to be something, and then this second one is going to be m plus 1. So we have to make 2 equations. So first, let's solve this equation for lambda. So we'll multiply both sides of the equation by d, and then we'll divide both sides by m. So the d's will cancel, m's will cancel. So now lambda is equal to d over m times the sine of theta. So that's the first equation. This one would be for m. Now what is going to be the second equation for m plus 1? Well, we would use the same thing. We would have lambda is equal to d, but now this is going to be m plus 1. And then that's multiplied by the sine of theta. But this theta and this theta, they are not the same, right? So this is the theta of m, and this is the theta of m plus 1. So now we have 2 equations, and we have 2 unknowns. So there's several ways that you could go about this. What we're going to do in this problem is we're going to set both of the equations equal to each other, and then we're going to solve for the different variables. So first we'll say that lambda is equal to d over m sine of theta sub m, and that is all equal to lambda d sine theta m plus 1 over m plus 1. This is the same thing as this right here, just a different way of writing it. Now what we're going to do is we're going to divide both sides of the equation by this. So when we divide this by itself, it'll be 1. So what we'll have is we will have lambda equals d over m plus 1 times sine of theta m sub m plus 1. And now just so I don't have to write it multiple times, let's erase this, and that is now 1. Our whole goal with this is to simplify this so that we're solving for the 2 equations with the 2 unknown variables. And essentially you can go in And we're going to cancel things that are the exact same. You just want to be really careful when you do this, because sometimes you can get yourself into trouble if you just jump in and say, oh, well, that's the same here, because they don't always cancel out. In this case, they do. So the lambda will both cancel and d will cancel on both. But algebraically, what's happening is I like to think of it this way. We're basically dividing by two fractions. We're going to say that this phrase is a fraction over 1 and this phrase is a fraction over 1. Well, what happens when you're dividing by a fraction? It's the same as multiplying by the inverse. So we can rewrite this as d sine theta m plus 1 over m plus 1. This phrase and this are the exact same thing. It's just written a little differently. So when we look at it that way, we have d sine theta sub m over m, and now we're multiplying it by the reciprocal of this. So we have m plus 1 over d sine theta m plus 1. So now it makes a lot more sense when we cross cancel. The d is the exact same for both, and the m's are different. And because this, you think of it as m plus 1, and this is m. So these are not the same. So these m's won't cancel out. So now when we multiply it straight across, we have sine theta sub m times m plus 1. And that's equal to m times sine theta sub m plus 1. And so now we want to get the m's on both sides of the same sides of the equation. So to do that, let's divide both sides by m plus 1. So now that will go away. And then we'll divide the other side of the equation, we're dividing by m plus 1, of course, by this. So we'll divide this side of the equation by sine theta sub m plus 1. So now that will cancel. So when we rewrite this, let's do it over here to give us space. We're left with m over m plus 1 is equal to sine theta sub m divided by sine theta m plus 1. So all of that work that we did was just to get to this point. And how we can use that is we are given these angles. So these two are equal to each other. We know what all these variables are. So we have sine of what is the first m? Well, it's going to be the lesser angle. Sine of the angle, and the first angle we said was 45.7 degrees. And we're dividing that by sine of the angle that corresponds to the m plus 1, which we said was sine of 72.6 degrees. When we go to our calculator and we plug this in, make sure that you're not in radian mode. So we need to go over to degree mode. Oops. Okay, so we're in degree mode now. And now when we plug this in, we have sine of the first angle, which we said was 45.7, and we're dividing by the second angle, which we said was 72.6. So that gives us 0.75. So what does that mean, right? That is what m over m plus 1 is. So let's round it to 0.75 and watch what we're doing here. 75, if we turn that into a fraction, is 3/4. So we just found that m over m plus 1 is equal to 3/4. So m in this case is 3, and the second order that for the angle that they gave us, the m plus 1, is 4. So that was a lot of work just to figure out that m equals 3 in this case, and then the second one is 4. Now that we have that information, now we can go back to our other equation, this one here, and now we can solve for the wavelength. So let's rewrite our two equations. So m of 3, that's lambda is equal to d over m. sine of the angle M, and our M plus 1, in this case we found is 4. That is lambda equals d M plus 1 sine of the angle that corresponds to the M plus 1 bright fringe. So now we have all the information. Lambda is equal to d, which we said was 1 times 10 to the negative 3 meters over the slits. There was 500 slits. And then we're timesing that by the sine of the angle, which we said was 45.7. All of that is divided by 3. If you write it right like this, it's the same thing. Don't get confused just because I wrote it this way. This one is the same thing, only in this case we have d, which is the same thing, 1 times 10 to the negative 3 meters over 500 slits, divided by m plus 1, which is 4. Now we have to use the angle that corresponded with m of 4, and that was 72 point. All right. So now when we go to our calculator, we have 1 times 10 to the negative 3 divided by 500 slits times the sine of the angle, which we said was 45.7. And then that all, need another parentheses over here. There we go. All of that gets divided by m, which is 3. So we have 0.477. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. So the wavelength for our problem is 477 nanometers. So that's the answer. There's only one wavelength, as the question talks about. We can go in and double check ourselves. And so we have the 1 times 10 to the negative 3 divided by 500 for d, divided by 4, and then we're multiplying that by the sine of 72.6, and lo and behold, we have the exact same thing. So we know that we did our math correctly, and the equations showed us that it's the same wavelength for these two angles for these m's of M3 and M4.